Yeah, thank you for joining me today, everybody. As she said, I'm Marc Kaminski, and together with my co-worker, Mr. Schlegel, I've been working on a machine learning pipeline for data-driven car diagnostics at BMW. So for those of you who have never worked with Apache Spark ML pipeline API, I think it gives you a good understanding why this talk will be a little bit important for you, because there are like 3 talks about similar topics today, and this just shows you why this might be important for lots of Spark developers. So we figured that the steps to build your own pipeline stages in Apache Spark were not that straightforward, and there were some specialties. And so I would like to welcome you to my talk about building custom ML pipeline stages for feature selection. I will start with a quick introduction into the project which my colleague and I are working on, which is data-driven car diagnostics. Then I will come to the point where we utilize Spark for our pipeline, and when we came to the point where we had to build our own pipeline stages for it. I will go through the steps for building a Spark ML pipeline stage for feature selection, and then I will show you how you can use this package in your own code, where you can find it, and what impact it might have on your own machine learning problem. So not finding the correct defect is a huge cost factor for car manufacturers. In fact, according to a study of consulting firm Bearing Point, it is the number 3 contributor for warranty incidents. So no trouble found cases are cases where a customer brings his car to a dealership and they don't really know what is the real problem, or they know what is the problem, but they don't really know the root cause. So they might do they might do the wrong switches, or they might just switch too much. So that results in ineffective fixing and to unsatisfied customers, because they might have to return for the same defect again. So we identified 3 root causes for that. First of all, the tools that we use today for, first of all, finding steps for doing diagnostics on cars, and the diagnostics itself are quite manual, and that manual approach can just not handle the vast number of possibilities that are present in a car anymore, if ever. And besides that, that is strengthened by the fact that cars are getting more and more complex due to hybridization, where we have several engines in one car, and the connectivity between the sensors in the car and the whole electrical parts. And then we have on the market side, we have evolving markets where there might be less experienced workshop staff, which cannot handle the manual tools that they use today. So we want to solve those problems by going with a data-driven approach. That means we just want to take the data that is in the car already, take that data from many cars, build models with that, and then use those models for predicting the defect in the dealership directly. And so the workshop staff can going to fix the car directly, immediately. So that will, first of all, we have automatic knowledge generation, which was done manually before. Then we can use that knowledge to perform workshop diagnostics, and this is also the first building block for performing predictive maintenance, which means that we can tell the customer while he's driving that he should go to the workshop soon. So to understand the design decisions that we made in our while building our pipeline, I would like to show you how our data looks like. So we have on the one side many cars, or like all the cars that BMW produces every year, that are on the streets from BMW, and we have on the other side many defects that can occur in different defects that can occur in some models and that can occur for all of those cars. And so we split that problem of all those cars into different categories of cars, and so which share the same defects. And then we build binary classification problems for each defect that might occur. So what you can see here, the first thing that is noticeable is that we have a huge feature space. That is like we have around 5 or further more thousands features for one data set. And those features can be everything from measurement values, extra equipment that is apparent in a car, and so on. And so we have a really heterogeneous feature space, which is a huge challenge. And besides that, the features are quite sparse. Sometimes only features are set for cars where a certain defect already occurred or some abnormality. And the third problem we have is that the data set is quite skewed. So we have defects only occurs in very little amount of cars if you take a look at the whole fleet. So those three challenges we wanted to solve in our machine learning pipeline. So we have the data on the one hand side and a predictive model on the other side. And we went with Apache Spark for doing the whole pipeline because it actually gives you the opportunity to do all those steps in one framework. Besides that, the size of the data set, which is several 100,000 of cars for one category of car, is already, and that coupled with a number of features is already exceeding the limit of some other frameworks like scikit-learn. And besides that, even if we could use those other frameworks, we would want to have a pipeline that is future-proof. So we expect that data to grow in form of more samples and more features. So Apache Spark was the best decision for this, or the best tool that we could use for this. So first of all, the data is loaded from the SQL database. Here, it goes through our ETL layer, which brings the data into a column format that is into a data frame that is used by Apache Spark. Then we conquer the challenge of the data skew by using some imbalance techniques like SMOTO, where you generate new samples of a minority class, or random undersampling, where you remove samples of a majority class. There's already, when this data goes through a preprocessing layer. Here, this preprocessing layer has several pipeline stages that are probably used in every Apache Spark pipeline, like the string indexer, which takes strings and assigns a numerical value to them, or the vector assembler, where a vector column is created for all the features. And then this data enters our cross-validation loop, where feature selection takes place and the classifier is trained. So we went with a feature selection approach since we wanted to know which features have a high impact on certain defects. So we can use that knowledge to think about the design of our cars maybe again, or solve some liability issues with subcontractors. And so the Apache Spark framework ML library only offers feature selection on chi-square based on the chi-squared test. So since we didn't want to lose any important features, we had to add some more metrics here. So the best way to do that is to add pipeline stages. So the rest of the talk will be about that. So for those of you who have never used the Spark ML library, and especially the pipeline API, I would like to give you a quick introduction. The most important interface is the pipeline stage, which bundles transformers and estimators. A transformer is a pipeline stage that takes data and transforms it somehow, and the estimator takes data, learns something from it, and then returns a transformer. So there's always a transformer for an estimator, but there might not be an estimator for a transformer because you can just have fixed transformers, for example, the vector assembler. Then, if you go deeper into the API, we can already find some of the most important pipeline stages that exist, or the interface for them. So there's the pipeline interface, which is used for concatenating pipeline stages. So you can train several pipeline stages at once. And then, since a transformer has to be returned by this pipeline, a pipeline model, the resulting transformer of this learning process is the pipeline model. So you can already see a similarity there, that always if you have a transformer that learns something from data, the model, or the name model is attached to the name of the estimator. Besides that, we have an interface for predicting pipeline stages, which is the predictor interface and which return prediction models. And we added our feature selector here as well, so into the Spark ML namespace. I will come back to the reasons for that later on again. So let's build this estimator and this transformer. So we built a common base class for feature selectors. So as I said, we built a common base class for all feature selection matrices that we would want to implement. So we have an abstract class feature selector. So the first thing that we need is we need to know what we want to return. So it is typed with the feature selector model. Besides that, we need some parameters which are defined in a trait called feature selector params, and they are made writable with the default params writable trait. A trait, for those who have never used Scala before, it's kind of like an interface for Java, but different. Like it shares the same idea, but it's a little bit complicated to go into this. So then, as you will see, the trait of a feature selector parameters only implements the getter methods for those parameters. So you need to add the setters here. The reason for that is that we want to concatenate setters. So the estimator or the transformer that uses this parameter needs to return itself. So we can concatenate those. The getters only return the value, so we can share those between transformers and estimators. Then the two most important methods for an estimator are the transform schema method. A schema is just a description of a data frame. So it tells us which columns are in it. It tells us which types those columns have, and then this transform schema method, it just checks if it has the columns that we would expect, if the types are correct, and if it succeeds, then it adds the columns that it would add to if the transformer that is created by this estimator. So this is used. So if you put several pipeline stages into one pipeline, first of all, what is done if you train this pipeline is that the transform schema method is called for all of the estimators and transformers in this pipeline, so you know early on if your pipeline will fail or not, and not after like a few hours of training. Then a little side note here. You can see that the features column here has several values, that is just a vector column. And so this data frame has a schema, and vector columns have metadata, which also tell us which columns are in it. This might be important. This is important for us because we want to know the most important features later on, and it will also be important later in this talk again. So just a little side note. Then the next, this is like the most important method for an estimator is the fit method, which takes data. Here, when we learn something from it, for our feature selector, we learn the feature importances and the most important features, and those are then stored in the transformer, which is then returned. Besides that, if you ever take a look at the code of this package, you will also find two methods called train and make. Those are not really necessary in an estimator, but you can also find them in different pipeline stages which are already available in Apache Spark as well. They just help us to avoid code duplication. So not really necessary, but neat. So but now let's get into the transformer that is learned by this estimator. It also it stores the selected features and the feature importances. then this transformer is made persistable with the ML writable trait. I will go into this again later on again. And we also have setters for those parameters that we would like to change after a transformer was learned. So for example, if you have a predictor and this predictor has a threshold for if it predicts a sample as true or false, you can set this threshold after learning to fit your needs. So it might make sense to add setters also to a transformer. Then we also have a transform schema method, which might or might not be the same as in the estimator. So for example, we don't need the labels in our transformer, so it's kind of different, but it still performs the same task of input validation. Then the most important method of a transformer is the transform method, which actually here it extracts the features that are the most important ones and adds them to a new vector column in our data frame, of a returned data frame. And then we have to also implement the write method, which was needed for the trait ML writable. So I talked a little bit about the feature selector params. So let's define them. As I said, we put our pipeline stage into the Spark ML namespace. So we can use code that is already available, which is marked private in this namespace. So for example, the has features call, the has output call, and the has label call, which are all in the param shared namespace, are marked as private at this point. They will be marked public in the future. But we wanted to reuse those and not copy all the code from there into our namespace. So that is why we, so to reuse those, for example, we put our pipeline stage into this Spark namespace. This also is, I forgot to mention that earlier on, is tolerated by the Spark community, so at least I've never seen anybody complain about that. And then we define all the parameters which are not predefined in this param shared namespace, which are needed by our transformer and estimator. So we use the param interface for that. The param interface is used so we can easily persist those parameters. They have a type, a value, a name, and a description. And there are already many params predefined for you, for example, for common types like the int, double type, and so on. But if you want to add your own types, for example, if you have a matrix parameter or something, then you need to implement a JSON encode and a JSON decode method in the process of adding this parameter. So this might give you a little bit of hard time, but it's needed to persist your parameters to disk in a JSON. So then, as I said, the getters can be shared between the estimator and the transformers, so we can put them here. So I talked a little bit about persistence already. So what do we actually want to persist? We want to persist the metadata of this pipeline stage, which are, for example, the UID, the timestamp when it was created, and so on. Then we want to persist all the parameters, and we want to persist the data that is learned. Here, those are the selected features and the feature importances. So how do we do that? Since we are in the Spark ML namespace, we can use the methods save metadata and load metadata for this. So this already gives us the possibility to save the metadata and the parameters. And for saving the learned data, we just create a data frame with the columns for the data we want to save on disk. And then we use the usual write parquet method to save this data frame to disk. And where do we do that? To do that, we create a companion object, which has the same name as the transformer, so feature selector model. So when we import the feature selector model to our application later on, we already have this object there available, and we can use the read method directly without having to import any other objects there. So here in this object, we implement the reading and the writing intelligence, which basically does what is explained above. So saving metadata parameters and the learned data, and then afterwards also to read back from disk. So how can you use that in your own pipeline? So the package is called Spark Feature Selection, and first of all, you import all the things you want to use in your pipeline. Then you load some data. So here the data is already in a vector, in a feature label format where all the features are in one vector column. Then you define all those feature selection methods that you want to use. So let's use, for example, a feature selection method based on the correlation between the features and the label, and one which uses the Gini coefficient between the features and the label. And then we can see that here we can already see that we concatenate the setters. So this is just the common API to create new pipeline stages in your code, to use pipeline stages in your code. Then, since each of those feature selection methods adds one vector column to your data frame, but we actually only want to have one feature column, we have to merge those features somehow. I created the vector merger for this, which you can also find in the package. This vector merger basically takes all the features from different vector columns and checks if there are duplicates, and if there are, it removes those duplicates, and in the end there's one vector column where all those features are merged in one vector column. So after that we put all of those pipeline stages into one pipeline, call fit on it. So what is done during the fit method is that the feature importances are calculated and the best performing feature importances are saved. So if we now transform the data set with this pipeline model, which is returned when we call fit, is that only the most important features are present in the selected column. So the Spark feature selection package offers several metrics and this utility stage, the vector merger, and you can find it on GitHub and on Spark packages. This slide is just for an overview. I won't go deeper into that. Then, does it always make sense to use feature selection in your pipeline? Definitely not. Sometimes it makes sense, or more often makes sense to use feature extraction, for example, PCA or LDA or something. But if it makes sense for you, then that's probably a use case where you have many features and you suspect most of those features to be redundant or not useful. So I want to show you the performance of such a data frame, which was created with the scikit method create classification data frame. Here we have 1,000 features and only 10 of those features have an impact on the label. And we built we built several random forest models of different sizes and performed feature selection before that, and I did one experiment where we did perform feature selection and one where we didn't perform feature selection. And as you can see is, first of all, if you have more trees, of course, the training time gets higher. But what you can also see is that if we perform feature selection first, the training time of a random forest becomes lower, which is obvious. Here, unluckily, the time used for feature selection is actually for one stage longer than for training the whole random forest. But still, still we have a better performance, classification performance, which is here measured in the area of under the precision recall curve and in the area of the receiver operating heuristics. So here and here, and so maybe we don't actually need all of those feature selection stages. So we checked what is the correlation between the feature importances calculated by those feature selection stages and between the random forest model. So we can see that the correlation selector, the Gini selector, and the information gain selector all have a similar correlation with the random forest importances, and we see that the chi-squared selector has a lower correlation. So since the correlation selector is the most takes the longest time, we checked if we remove it, if it's still if the performance stays the same for our the classification performance stays the same. So we did that, and as you can see, the performances stayed the same. So this is not just the same values. We actually did the experiment again, and since we performed it several times, the mean performances stayed the same. And what we also can see is that now the training times becomes much lower, or much like twice as fast as when we don't perform feature selection, and we get a better performance. So in this use case, using feature selection makes sense, but you definitely have to evaluate that for your own data set. So this is actually, oh, you can see it. Yeah, well, sorry. So this bar goes till here, and this bar goes till here, for those of you who can see it. So that is also, like, knowing what you do is always a good lesson. So this was also the lesson we had to learn while using Apache Spark. So you need to know what your data looks like and where it is located. That means, for example, that sometimes operations can fail if you first work in local mode and then go to a cluster. So think about where your data is located, how it looks like. If you do caching or caching, think about if your data might completely fit into the memory. So you might want to use the persist method and not the cache method, because the default method for cache is that it stores the data into memory and disk, and which might take longer. So what you should you can evaluate those things in the Spark web user interface. If you think your Spark jobs run too long, use that to find out where it takes too long. And yes, so, and the last point is that you should not reinvent the wheels for common methods. So as we did, consider putting a pipeline stage into the Spark ML namespace. Most of the other challenges that we faced were based on several gyras, and they are already addressed or will be addressed in future Spark releases. The most important one was a column limit, which was introduced by a gyra, but yeah, you can ask me about that later, or Google it yourself. Otherwise, I want to emphasize the steep learning curve that we had with Apache Spark. I personally started using Apache Spark this year, and after overcoming most of those early pitfalls, it really has become a great framework for working with medium large data and of course larger data as well. For us, medium large data, and in other talks, large data. It has a very concise API, which becomes very natural to use with the Scala API, and which you will especially explore if you build your own pipeline stages. So I can only recommend doing that if you build your own pipeline. So thank you for the attention, and if you have any questions, feel free to ask them now or ask us via email. Yes?
I'll run to the mic.
Hi, thanks for your talk. But I wonder, in your business case, why you use Spark instead of sklearn? I don't know how large is your data set, but let's suppose you have 2 million cards, and maybe the data can be easily fit into 64 gigabytes servers. Then sklearn has already provided existing feature selections, and maybe it's even faster because in such a in-memory computation.
Yes. So first of all, yes. So first of all, it just makes it easier to work with this amount of data to use Spark, in our opinion, because first of all, the concise framework, and second of all, we want it to be future-proof, so we expect that data to grow, and if we already are on the right horse, that's easier to be future-proof. Does that answer your question?
Any other questions? We have time for one more. If not, let's give Marc a, oh, sorry, last question today.
Hi, thanks very much for this nice presentation. I just didn't get how you actually set the label in your very last stage when you actually send your feature space.
Oh yeah, so since our label column is called label, so the default label column name is label, so I skipped that to fit it into the line.
All right, let's give Marc a warm welcome, or sorry, warm applause.
Yeah, thank you.